Today we're going to talk about graphing sine theta and cosine theta. Now these graphs are parent functions. You might recall that from lesson 1 in functions when we talked about the parent functions like y equals x squared, y equals the root of x. Same thing, these functions are parent functions. Now being parent functions, it means it's the most basic form of the graph. We will be doing transformations, and we will be talking about all of the ways the transformations are going to affect your curves, and that's for a little bit later. In this lesson, however, I'm going to go over the basic function sine theta and cosine theta, and then going to do a couple of little examples from your homework, and at the end there will be a video that I found on YouTube. I'll give you the link to it to show you how it all unravels. It's really quite beautiful. So in your textbooks, they do not really talk about the unit circle, but I think it's critical that you understand it in order to figure out how the graphs actually function. So I'm going to talk about y equals sine theta and cosine theta using this unit circle. So what is a unit circle, first of all? Unit circle is a circle that has a radius of 1. So if you see here, if I go across from here to here, it says the coordinates are 1 and 0. And up at the top here, it's 0, 1, minus 1, 0, and 0 and minus 1 down here. So when we did primary trig ratios, sine theta, cosine theta, when we said what sine theta was, and we're going to write it out here again to jog your memory a little bit, sine theta in terms of x, y, and r was y over r. And cos theta was x over r. Now, what happens if we're using a unit circle and r is 1? Well, that just means that sine theta would be y and cos theta would be x, right? So we actually end up with coordinates cos theta, sine theta, because if r equals 1, okay, so I have y is sine theta, x is cos theta. So we have coordinates, cos theta, sine theta. So anytime I go, and remember that was just like if we dropped a perpendicular here, and this would be y, this was x, and this was r, and our theta was in here. So we talked about that a long time ago when we did when we did primary trig ratios. So that means that each one of these pairs of coordinates represent the cos theta and the sine theta for whatever the degrees are here. So as I go around the circle, if I said the cos of 30 degrees would be root 3 over 2. The sine of 30 degrees would be 1/2. Now, your teacher may ask you to graph according to making a table of values. So your table of values would include all these values. So let's say I was doing a sine theta graph. So I'd say 0 degrees is 0, 30 degrees is 1/2, 45 degrees, root 2 over 2, 60 degrees, root 3 over 2, and so on as I go around the circle. So that's all this unit circle represents, is cos theta and sine theta for each of the angles that you're talking about. So as you go up to 45, now these values inside here, these are radian measures. It's just another way of measuring an angle, and you'll do that in grade 12. It just means pi here represents 180 degrees, so 180 divided by 6 would give you 30, and so on. But don't worry about that till next year. What you need to understand, though, is that each of these represents cos theta and sine theta. So if I wanted to graph sine theta, so I'd say sine of 0. So let's just write out a couple of values here. So we'll do sine 0 degrees. So the sine of 0 degrees, that's this value here. So I'd say 0. That's the height of the function, right? Okay, so what's the sine of 30 degrees? So you go up here, and it's this value here, 1/2. So this is your y value. And so on and so forth. You would have done, oh, I skipped the 45, but that's okay. you would do a whole table of values of these, and then you would graph them. So let's put the unit circle aside here. Excuse me, a little bit of a frog today. I haven't talked enough. So if I were to graph these values, let me just pull this back here just for a second. So you'd see that I would start with a graph of y versus theta. And if I go all the way around the circle, all the way around here, that's 360 degrees. So when you go to graph your sine functions, you always want to divide your graph into 4 equal parts. So I usually draw it like this. If you don't have graphing paper, just make a line, cut it in half. That gives you 180. Cut that one in half again. That gives you 90. And 90 and 180 is 270. So you want to have it nicely spaced. And as you know, our maximum value for sine theta is 1. Now, do you remember why? Well, that's here, right? The sine of theta, the maximum value would be 1 here. The minimum would be -1. Remember that sine theta and cos theta never go larger than 1 because we're always doing the opposite over the hypotenuse or the adjacent over the hypotenuse, and the hypotenuse is always longer than either of these two sides. That's why the ratio is less than 1. Okay, so if I were to graph sine y equals sine theta here, you could put in all the table of values and you would have something like this. So it goes 0, 90, 0, it's not 90, sorry, 0, 1, 0 to -1 to 0. So it's going like this. And you try your best to make it nice and curvy. Do not make pointy tips on here. This is a nice round curve. And it keeps going on because it's sinusoidal. It could also go this way, right, if I went the other direction. So the other thing you can see from this sine theta function graph is that between 0 and 180 degrees, sine was positive. Now that should make a lot of sense to you, given the cast rule that we've already looked at, that said that sine was positive in the first 2 quadrants. So see, it's positive, and then it's negative under here. How beautiful is that? Okay, so the period for my sine theta function means how long before it starts to repeat, and you can see that obviously it's going to be 360 degrees because it is a circle. 360 degrees. What is the amplitude? Well, the amplitude is 1. Don't say plus and -1. That's for the range, right? The amplitude is simply the distance from here to here. Amplitude, 1 unit. The domain, well, domain is theta is an element of real numbers. Real numbers, why is it real numbers? Because we can put in any value for theta here, and we can get all sorts of values for, I could ask you what's the sine of 100 million, and basically you could find it. So because this is continuous, it goes on and on and on, it doesn't stop. What are the zeros? The zeros between 0 and 360 degrees would be 0, 180, and 360 degrees. Now, it would also continue. Usually when you're asked for the zeros, they have to give you some sort of domain. What are the zeros between 0 and 360? There I have 3 of them, but they are also a multiple of 180, right? Times 2, times 3, times 4, times 5. What is the range? The range goes from how high and how low does it go? So the range is this part now, right? From here to here. So that's when you have your plus or -1. So the range is -1, less than or equal to 1, y less than or equal to 1. So it goes from plus to -1. Now, if you forget what the sine function looks like, it's very easy for you to grab a calculator and say, what is the sine of 0? So you know where it begins. Okay, so let's take a quick look back at the unit circle to see the cosine function. So remember that cos theta now is going to be my x coordinates. So it goes from 1 to 0 to -1 to 0. All the x values. Those are your cos values for the different angles. So again, your teacher might ask you to write out a table of values, and you might have to go through, 30, 60, 90, 120, 150. You could find all these little values in between. You can find an infinite number of points if you want, but I'm sure you don't. And again, if I looked at it, it said the cos of 0 was 1. And then at 90 it goes to 0. At 180 it goes to -1. What am I doing here? That's right. Back to 0 and up to 1. The easiest way to draw these, the cosine functions start and end at 1. So that means your lowest point has to be in the middle. The other two are on the axes. So you can see there's only 2 zeros for this one. So my graph goes like this time. And that's your cosine function. So if you look at the cosine function, you can see that it's the same as a sine function. Like I could continue this over here, couldn't I? I could keep going. And this is where it gets confusing unless you're told what kind of function you're looking for, because the sine and cosine function can be just a horizontal translation, right? So if I move this sine function here, if I moved it to the left 90 degrees, it would be here. So how do I know if it's a cosine function or a sine function? And basically, it's up to you to, or your teacher to tell you what function it is, or sometimes you're asked to describe it as both a sine and a cosine function. That may sound a little confusing, but that'll straighten out as we get into more graphing. Okay, so the period again, well, it's still 360 degrees. Remember, we went all the way around the circle. It has the same amplitude as the sine function. The domain is the same. We can put in any value for theta here. The zeros, there's only 2 between 0 and 360 degrees. And the range is the same as the sine function. Okay, so it goes from +1 to -1. That's your range. So it's really important that you spend a bit of time understanding how to graph these functions. Make sure you can sketch them quickly, because it's going to you're going to do a lot of it. Now, if we look at this function as it represents into the cast rule again here, C-A-S-T. So this is 0, 90, around we go, right? You can see that it starts as positive, and then from 90 to 180, sine was positive, cos was negative. Cos is still negative in quadrant 3, but cos is positive in quadrant 4. So that's how it all relates. Okay, so what I want to do for you is a question number 3 that is in your textbook on page 360. And they give you a displacement. Let me just pull it up here. It says, a boy rises and falls as it rides the waves. A buoy, whatever you call them. The equation h at t equals cos 36t degrees models the displacement of the buoy ht in meters at t seconds. So it's going up and it's going down. They ask you to graph the displacement between 0 and 20 seconds in 2.5 second intervals. So what you need to do is a table of values. So you're going to have t, and you're going to have h at t. And you would make a nice table of values like this. And you would plug in 0. So the cos of 36. Now you're plugging in 0 for t here, okay? It's not that confusing. You plug in 0, so you have cos of 0, and the cos of 0 is 1. So then you would do, what's the cos at 2.5? Now I did these a little bit earlier, so I would have a bunch of values for you. Cos of 0 was 1. 2.5, you can do this on your own, but it goes to 0. Let me just write out the first few. Minus 1. 7.5 is 0. 10 is 1. 12.5 gives you 0. So you're just plugging these into your calculator, okay? It's not a big deal here. 15 is minus 1. Okay, now that's as far as I'm going to go because I'm going to sketch it for you and you're going to see a pattern already. So 0 and 1, 2.5 and 0. I'm going to do it in red so it shows up a little better. 2.5 and 0, 5 and minus 1, 7 and 0, 10 and 1, 12 and a half and 0, 15 and minus 1, and then it's going to go like this. Anyway, I'll just sketch it in. Okay, so it's going like this. Now try to be smooth. I know it's really difficult, but you'll get better at it. Okay, so that's what the graph is going to look like. This is the displacement of some boy as it goes through this cycle. So it's rising and falling in the waves. Now the waves must be pretty steady for it to be so exact, but now the question said, B says determine the period of the function. What is the period of this function from the graph? So it goes down and back up again. So when you figure out the period can be measured from 2 troughs like this. So here's the period. Or you could measure the period from 2 peaks or 2 troughs. Or you could measure it from one complete cycle, say from here. So you could go from here to here. Either way, you're going to see from here to here is 10 seconds. From 5 to 15 is also 10 seconds. So the period is 10 seconds. What is h at 35? Well, that's just like what we're doing here. So you would plug h at 35. Remember your function notation? So that's the cos of 36 times 35 degrees. And you might be able to figure out what that's going to be, knowing that the period is every 10 seconds. So 35 minus 10 would be 25, minus 10 would be 15. So if I look at what 15 is here, that's going to be the same as at 35, right? Because every 10 seconds it repeats. 5, 15, 25, 35. So you can plug it into your calculator, or you can use your head and say it's going to be minus 1. Now this part here requires a little bit of calculation, and it's a good basic practice question for some of the other word problems where you're going to have to find a height at a certain time. So the question says, when does the displacement first reach minus 0.8 meters? So minus 0.8 meters, if we look at the graph, it would be somewhere around here. Let me see, this would be minus 0.8. So I'm looking for something between 2.5 and 5 seconds. So you can do that using your calculator, believe it or not. So I'm going to put, when does this reach this height? You did this kind of work in grade 10 with quadratics, right? When is cos of 36t equal to minus 0.8? So on your graphing calculator, not graphing calculator, any calculator, if you do the inverse of this, so cos negative 1 of minus 0.8, that's going to tell me how many degrees this has to be, right? That's going to give me this value. So if you do, let's see here, second cos minus 0.8, I get 143.13 approximately degrees. So this was degrees here too. So 36t has to be 143. 36t is equal to 143.13. So t is approximately equal to, so all I have to do now is divide 143.13 divided by 36, and that's going to give me the time. So it's approximately 3.97, and and that's even more, approximately 4 seconds. So once you've done a calculation like that, you want to go back and just look at your graph to see if that makes sense. Well, you could even look at your table of values. So 3.9 or minus 0.8 is between here and here. And we also said it was going to be between approximately here. So that makes good sense that 4 seconds is a proper solution. Now, one last thing. There's some other questions in your textbook a little later on. Question 9, they say, where are all the values when cos theta is -1 between 0 and 360 degrees? Well, that's pretty easy. There's only one, right? This is the only place that it hits -1. But you can see that there's going to be 2 values for any other point. Like, let's say, I said, when is it going to be a half? And you go like this. You'd say, oh, it's going to be half right here. It's going to be a half right here. Oh, isn't that clever? Quadrant 1, quadrant 4, where cos is positive. That's where it would be a half. Okay, so that's pretty much what covers in 6.2. I'm going to put a link to a little video here for you that is going to show how these graphs come out. It's really cool. I love it. Hope you like this lesson. Give me a thumbs up, subscribe, and see you in the next lesson. Bye.